Right. Good evening, everybody. Thanks for attending our joint event between ICorr Aberdeen and AMPP. And welcome to our May 2024 webinar. Today's presentation is on proportional hazard values for different pipeline coating types used over the timeline from 1900s till now by our presenter, Susan Jacob from OneGas. She's currently located in the US right now. And next slide, please. This is our 2023-24 Aberdeen Branch Committee, and we are still currently looking for at least 2 committee members. If you're interested to join our committee, please reach out and I'll arrange a chat with you. Next slide, please. And thanks to our branch sponsors. Next slide, please. And our next branch program is going to be on the last Tuesday of June, and the topic is metallographic replication of in-service plant by IRIS NDT. And also we're going to have our 15 minutes AGM before the presentation starts. Next slide, please. And for our speaker today, it's Susan Jacob. She's a senior pipeline integrity engineer in asset management for OneGas, which is a natural gas distribution in the US, where she has currently worked for the last 5 years, covering Oklahoma, Kansas, and Texas. Susan previously worked with ConocoPhillips in Aberdeen, UK, for 6 years as an integrity engineer, and she has completed a master's in subsea engineering in the University of Aberdeen in 2016. During her free time, Susan loves working with people from different culture and outside work. She loves exploring new places and going to rustic camping with her family. So let's put our virtual hands together for Susan, and I'll hand over the floor to you. And please, if you've got any questions, please put it into the Q&A box, and Susan will address it at the end of the presentation. Right. Thanks. Over to you, Susan.
Thank you for having me for this event. I live in Tulsa, Oklahoma, and the company I work for is over 100 years old. Over these years, there's been many acquisitions, spin-outs, takeovers within the company, and this has led to us inheriting multiple vintage pipeline systems with different coating types and poor historical records. So as part of reducing risk in the system, uh, different efforts have been taken for, especially in the area of recording different coating types and determining their performances. Recently, I worked on a project in studying about these coating types to determine their proportional hazards. These considerations will then eventually be put into the company's risk assessment model, and this final model results will aid the prioritization of inspection, maintenance, and replacement work plans. These are some of the topics that we're going to be discussing today. Where the focus and intention is mainly to develop and promote the company's core values, which are safety, integrity, ethics, service, and value. This project is focusing on specifically safety and integrity. Such projects normally improve overall safety measures in our system by reducing the risk of failure. In this presentation, I aim to give you a thought process in coating performance ranking that will help to meet regulatory requirements and maintain a robust risk model. Some of the topics we'll be covering are PHMSA threat and consequence considerations, and more closely, external corrosion threat-based likelihood model. In order to give you a background of a coating performance, let's look at it, what was done historically. 1859 saw the use of metallic pipes, mainly wrought iron, for oil transportation after drilling of the first commercial oil well in in Pennsylvania. By the 1920s, some of the operators started to coat the pipe while being laid in the ditch. This was an attempt to protect it from corrosion. The idea was to build a barrier between the pipe and the corrosive conditions in the soil. Some of the earlier coatings that have been used are coal tar and phosphate, and this was applied basically by pouring and hand mitt and rag application. Though this is a primitive technique, it helped in reducing corrosion. In 1943, NACE was established by 11 corrosion engineers in response to high levels of corrosion failures reported on pipelines. The intention was to reduce risk and provide standards and education on corrosion control in pipelines. The first plant applied uh, coating system was developed in the 1950s. This was a major advancement in coating technology. Prefabricated, fully coated spools were now available, with only the field joints requiring over the ditch coating. By the late 1950s and early 1960s, liquid-based epoxy coatings were introduced into the system, and in addition to polyolefin materials, polyethylene or polypropylene were also used. The 60s saw the birth of mainline coating systems called as fusion bonded epoxy. Many of you must have already heard it because we're still using them in our systems. It provided excellent flexibility properties, although single application of FBE was only used in standard applications where environmental conditions were not challenging. So in order to compensate that, dual layer FBE systems were introduced, which helped in developing abrasion resistant properties. Some of the field applied coatings that we use these days are liquid coatings, tape coatings, wax coatings, and concrete coatings. After considerable research for a coatings development timeline that aligned closest to our company coatings, I came across a book on pipeline coatings by Y. Frank Chen and Richard Norsworthy, published by NACE International, which I've been using as a reference to help me understand as well as aid towards doing a desktop evaluation of pipeline coatings performance. As given in the slide, this timeline is a generic one that can be used as a benchmark to identify where a company timeline for pipeline coatings fall. This timeline was drawn from historical records, that is data sheets representing Shaw's pipe timeline. That is a company called ICorr, which is Canadian, is known to be a global leader in pipeline coatings and integrity management. On this slide, I will explain broadly three main coating types that we currently have in our system. One is coal tar enamel, which was used between the 1940s and 80s, asphalt, which was used between 1950s and 70s, and fusion bonded epoxy, which are used even in these days. Coal tar enamel is a polymer-based coating produced from plasticization of coal tar. It is known for being low in susceptibility to coating holidays. It also has low current requirements. It has good resistance to cathodic disbondment and has good adhesion to steel. Asphalt coatings, also known as bitumen, are generally derived from petroleum refineries after crude oil distillation through a vacuum distillation unit. It is generally considered a byproduct of residue of refining processes. Like coal tar, it was initially a field application and progressed into a factory application. Its application characteristics are similar to coal tar, but they are prone to stress corrosion cracking. Factory applications like fusion bonded epoxy is an epoxy coating which is plant applied to preheated pipes approximately at 232 degrees centigrade and 450 Fahrenheit, and it's used using fluid bed, air spray, or electrostatic spray methods. Some of the advantages are um, it has an excellent adhesion and corrosion resistance. And one of its primary advantages are that it does not hide apparent surface defects. So these defects can be minimized by increasing the thickness of the coating. Some of its drawbacks are that it has high moisture absorption, and it's not very resistant to mechanical impacts. It can be easily damaged during transportation or installation. Hence, dual layer FBs are used, which provides a first layer that is a base coat and over the pipe surface directly, and then a second layer is applied that is a top coat over the base coat before its gel activation time. The dual layer FBs are commonly used in pipes that undergo directional drilling for especially for road and railway crossings. So during the installation, the pipe is pulled through a hole supported by drilling mud where coating abrasion and scratching can occur. So the application of a dual layered FB coating can mitigate the damage to the base FB during installation. This prevents gouges, mechanical damages to some extent. Some of the disadvantages though are its application cost is quite high, and its limited historical data availability for measuring performance. Uh, Similar to HSC, the US has a Department of Transportation Agency known as the Pipeline and Hazardous Materials Safety Administration, or also commonly known as PHMSA, which is responsible for developing and enforcing regulations related to safe, reliable, and environmentally sound transportation of energy and other hazardous materials. While HSC is UK's national regulator for workplace health and safety, covering a wide range of industries, including agriculture, PHMSA is a federal regulatory body solely dedicated to safety and regulations of pipelines on a national level. In addition to PHMSA, we also have state level regulatory bodies specifically to the states that our company covers. It is Oklahoma Corporation Commission, Kansas Corporation Commission, and Texas Railroad Commission. Both federal and state bodies carry out regular audits to ensure operators are adhering to code requirements. Moving on to failure analysis and risk methodologies. We all know that risk is mathematically defined as the product of a probability that a failure can occur and the consequence that consequence that results from that failure. We all must have come across various risk models varying with degrees of increasing degrees of quality. That is relative risk model, quantitative risk model, or a probabilistic risk model. A relative risk model offers a risk score based on a collection of scores from relevant factors, while a quantitative risk model, sometimes referred to as a QRA, provides a numerical evaluation of the levels of results. It helps estimate quantitative outputs for likelihood and consequences and represents the outputs in standard units like frequency, probability, and expected loss. Probabilistic risk models are recognized by the industry as the best practice. Probabilistic risk models are designed to provide the probability of failure and the associated degree of consequence expected in a in a failure event. The results of a PRA can be used to define the probability of the costs associated with a failure. The model logic is that it attempts to adhere to laws of probability. We must have come across at some point in our career statistical distribution models like Monte Carlo simulation or Weibull distribution. These are some of the distributions that are used to determine probability of failure due to specific threats. PHMSA identifies broadly 8 threat considerations. We will be going through them briefly in the next slide. In addition to threats, it also considers consequence categories. Some of the consequence categories stated here are health and safety, which takes into consideration injuries, fatalities, and in some cases, weather conditions. Uh, Next is direct economic loss, which includes service disruption, property damage, commodity loss, response and repair cost. Regulatory impacts include technical as well as economical impacts, which is fines or notice of probable violation. Environmental impacts, as the name suggests, impact to the environment as well as extent of cleanup required. Corporate image reputation, this plays specifically because we are a gas company, and we have a reputation which could in the event of a failure, it could be a negative public exposure, reputational damage, or social impact, that is positive or negative perception of the gas company. PHMSA considers various threats to pipeline safety, which can be categorized into 3 main groups, that is time-independent threats, time-dependent threats, and resident threats. Time-independent threats are threats that do not significantly change over a period of time, but they are often unpredictable. Examples of these kind of threats are external corrosion, internal corrosion, manufacturing and construction defects, equipment failure. This is particularly in relation to pipeline components like valves, pumps, etc., due to wear and tear or malfunction. Time-dependent threats are those threats that tend to grow over time and require ongoing monitoring. Examples of these are stress corrosion cracking, fatigue cracking, hydrogen-induced cracking, environmental stress cracking. Finally, resident threats are those that do not grow over time but can be influenced or may act when influenced by other conditions or failure mechanisms. Some of these examples are mechanical damage, geotechnical hazards, natural forces. As our company is in the tornado alley, and this region is prone to earthquakes as well as floods. A comprehensive risk assessment process considers all these threats that we have identified here to ensure interactions to ensure and their interactions to ensure pipeline safety. As we have seen, the threats that contribute towards risk of failure. Operators are continuously evaluating and improving risk assessment approaches based on facility design, environmental knowledge, and experience. One approach to accomplish this is by considering the overall risk in a system as the sum of mitigatable risk and residual risk. Some threats that can be mitigated are corrosion, equipment failure, material or joint failure, while the non-mitigatable threats may be excavation damage, incorrect operations, or natural forces. PHMSA has been collecting pipeline incident reports since 1970s. This extracted dataset sample provides us an in-depth understanding about the causes, sub-causes of the incident. The pie chart that you see over here shows you all recorded natural gas transmission pipeline incidents over a period of 10 years, that is 2010 to 2020. There were 1,364 incidents, and the threat causes have been identified in numbers and percentages within this pie chart. Looking at the big drivers for failure, we can see that corrosion comes second with approximately 20% over a period of 10 years, which is roughly 13 incidents every 6 months. Diving down a bit further and looking at the sub-threats within corrosion, we can see that there are more than 36% corrosion threat incidents that are caused due to external corrosion in the span of 10 years. External corrosion is a contributor to mitigatable risk. Hence, mitigatable measures can be put in place to ensure that the risk of an incident occurring with external corrosion can be reduced. In order to measure and evaluate risk in our pipelines, efforts are being made to move from a relative risk model to a probabilistic risk model, which expresses capabilities to incorporate data uncertainty through input distributions, quantitative inputs, and outputs, and help identify current risk drivers across the system, leading to targeted preventative and mitigative measure selection. To determine uncertainties, one such model that we use is the Weibul's proportional hazardous model. This aids in evaluating threats in our system. The Weibull proportional hazardous model is a statistical model, and it's used to understand the relationship between the time until an event occurs, such as a failure, and one or more predictors. It extends the Cox proportional hazards model by allowing the baseline hazard function to follow a Weibull distribution, which provides flexibility in modeling the hazard over time. So what you can see here is a proportional hazardous model equation where h of t is the hazard rate, that is the likelihood that the asset will fail at age t, given that it has not failed yet. So this is a proportional hazardous model which has incorporated the Weibull distribution into its equation. So the Weibull distribution aspect of it is the beta, that is the shape parameter of the distribution, as well as the eta, that is the scale parameter of the distribution. The shape parameter of the distribution determines whether the hazard rate is increasing or decreasing, while the scale parameter is the actual magnitude of the hazard rate, and the T0, the time after which failure starts to be observed. So as you can see over here, there's two parts of this equation. The one section defines the baseline failure rate for the entire asset population, and then the second part um, is a factor that can be added to the baseline failure rate in order to adjust it. So we'll look at this closely in the next slide that we're going to in regards to corrosion threat. Each threat will have a base likelihood model. So for corrosion threat, to adjust the baseline failure rate, that is this this part of the equation, certain factors are considered, and that can be incorporated within this exponential function. These factors are age, length, length of the pipe, coating type, and leak history. All these factors are available to some extent, except for the performance of each coating candidate system. I had to do a research on coating performance to determine ranking prioritization between the candidate systems, and a coating factor then will be determined from this ranking, thereby giving us a proportional hazardous value. What you see here is a top 10 coating types based on age, chemical composition, uses, advantages, and disadvantages. These conclusions were based upon the research from various sources, predominantly pipeline coatings by Frank Cheng and Richard Norsworthy, published by NACE International. I've also reviewed a sample set of coating types in our company based on their durability and condition. During my research on different coating types in our system, I came across a unique coating system called bituren, not commonly available but existing in our pipes. It was used in the 1930s, and limited information has been available apart from the oil and gas clipping that you see here, and it's mentioned in the 19 and in a 1957 report from the U.S. Department of Commerce. In this report, it says that bituren enamel consists of a combination of coal tar and asphalt. This was manufactured by a company called Hill Hubbell and Company. One of the layers of this coating involves asbestos felt, hence, precautionary measures are taken when digs or other interventions are carried out. In conclusion, the research on coating types is an ongoing effort in our company across the three states, Oklahoma, Kansas, and Texas, which involves years of effort to determine the coating type of our pipe as the age varies from the 1900s to today. As a company, we are still in the process of creating a coatings timeline specific to the three states, operating over 2,300 miles of transmission pipelines, and this is not including our distribution system. And this varies from with varying install dates from the 1900s. To put it into UK perspective, this is equivalent to going from Land's End to John O'Groat and back approximately twice. Ideally, it is recommended by Frank Cheng and Richard Norsworthy pipeline coatings that the best way to determine if a pipeline coating system may provide satisfactory service under variable conditions, that is, during its life cycle, is by replicating it in the laboratory and accelerating the process to see if there is any differentiation between the coating candidates, and then thereby establishing a ranking prioritization between them. As this method has not been possible, efforts have been made to refer to the standards for external coating materials and applications identified in the pipeline coatings book for the coating types that are in our system, and in addition to that have compared uh, performance compare the performance between the different coating types in our system based on leak history, age of the asset, and cathodic protection. Thank you.
Um, Thanks, Susan, for the very interesting presentation. If you've got any questions, please put it